We now extend our idea of computing volumes with slices to the most generic kind of shape here, the generic shape of a cone. We're going to keep some variables flexible. We're going to have a height. We're going to call that h. And the bottom radius will be r. And it's going to be very important to carefully define our variables here. The most common mistake people make is to mistake these h and r, which are constants, with the variables of integration, which are the height and radius of the slices we're going to take. So, how would we take our first step and decide on how to slice this object up? Well, I think the most obvious way, or the simplest way to slice this object up, is to slice it horizontally. Because if we slice it horizontally, we'll end up with what shapes? Well, if we slice horizontally, we're going to end up with thin little cylinders. And so we can talk about the volume of one slice. And it's a nice constant area shape. So it's going to be the area of the circle times the thickness. We get 3 dimensions, 1 for the thickness and 2 for the area of the circle. And now we have to start defining some variables of our own. We want to find the volume of a generic slice, so one somewhere in the middle of this cone. How are we going to find that? Well, we're going to define the volume to be, well, let's call it y. Let's call this distance here from the peak to our slice here. Let's call that y, and that makes the thickness of each slice delta y. Notice I can't reuse h here. H is already a constant, and I can't talk about the slice at height h if the whole entire cone has height h. So it's important to define a new variable. Likewise, we need to worry about the area of the circle. So the thickness is good, delta y. Now we need to imagine the area of this circle. Well, for that we need the radius, and we already have an r, so let's not use r. Let's call it, we've used y, let's call that x. This distance here will be x. If we're interested in that x value at a slice at height y, how are we going to find that? Well, we can take advantage of similar triangles. We have height y, and this is the x that we want, is the radius of that slice circle. And we also have our big rectangle, or sorry, our big triangle here with height h and radius r. And so by similar triangles, we really want to know the radius of our slice. So we're going to look at x, and the x to the y value, that ratio is going to equal the r to the h value. And if that's the case, then x is simply r over h times y. Okay, so we go back now to the volume of one slice. It'll be the area of the circle times the thickness. The area of the circle is pi r squared. Oh, wait, radius of the circle we're slicing at, so it's not r, it's x squared in our definitions, and the thickness is delta y. Now we're going to be integrating in a second, and x needs to be related back to y, but fortunately, we just found that relationship through similar triangles. So as we imagine different slices, each with a different y, we're going to have different circles. Those circles are going to have different radii, and the radii x are given by this formula here. So we can replace our slice volume with the x in there with this r over h times y. And that was all squared before, so it's squared here, delta y. And again, that's the most challenging part. If our next step is simply to add up the volume of each slice, and we're going to do that through an integration step. We'll do that on the next page. So our total volume is approximately adding up the slices, which were pi r over h times y squared dy. Remember, y is the height of an individual slice, h is the height of the entire cone. H is constant, y would change as we take different slices. And if that's the case, we can get it exactly equal to replacing the sum with an integral. Sorry, this should be a delta y still right now. And replacing it when we turn it into an integral, taking finer and finer slices with dy, then we get pi, let's actually expand this out, r squared over h squared times y squared. And where do the slices start? They start at the peak, that's y0. When do they end? Well, when we slice, 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 when our y value gets all the way to h. So this is where, another place where h appears in our calculation. And remember, it's the constant. What is the height of the cone we're looking at? Now we're at the stage where we can simply integrate. Again, reminding ourselves that this is the most challenging part, is the setup. The actual integration stage here is quite straightforward. We remember that r and h here are constants, so they can go out front, r squared over h squared. And we're going to integrate, oh, pi is a constant too. So we just had the integral of y squared. What could be easier than that? We have pi r squared over h squared here, and the integral of y squared is y cubed over 3. We're going to evaluate that at h and 0. And we keep going, copy the constants. So we're going to get h cubed over 3 minus 0 cubed over 3. And that gives us pi r squared over h squared times h cubed over 3. And the only things we can cancel are the h's. We've got h squared here. We'd subtract 2 powers from the top. And so we'll get pi r squared h over 3. And for those who know the volume of a cone, this is exactly how it can be derived. I think it probably was derived originally. Pi r squared h over 3 is the volume of a cone, and we found that by developing an integral that represents the volume of each slice, and then the integral takes care of the sum of adding up all those slice volumes to get the total volume of the cone.